Okay, physical science time. Today we are talking about bonding and chemical formulas. Bonding and chemical, please write this down. I'm going to put up here, this is the correct pluralization, or maybe like the old-fashioned pluralization, but it's the one I think is correct. This word says formulae. You pronounce the AE at the end as E. People nowadays do often say formulas when they're talking about multiple formula. One formula, multiple formulas, but it is the old-fashioned way, as I say, and I would say I like it better, the correct way to name multiple formulae with an AE at the end, which is plural. What would like this? Hey, someone at your table should have your book out so that you can read the words that I'm writing in a way that I obviously can't. Formula is formula, add an E at the end, and that makes it formulae. And please, I'm always amazed when I look up and say, stop talking, at who is talking, because it just cycles every time. It's a different person, and it's never someone I expect. I'm just going to say, Carson, stop talking, but it's not always Carson. The first time it is, and then it's someone else. Stop talking, listen. Formulae. Some people would say formulae, but that's not the correct way to pronounce it. Formulae is correct. Bonding. We talked about this already. Remind yourself, this is a review, but remind yourself that there are more than three, but there are three broad categories of bonding. Listen for me. Tell me one, someone who raises their hand. Ty, what's one kind of bonding? Metallic. Metallic bonding. Okay, there's another one. Ionic, says Kesson without raising her hand, but that's okay, thank you. And then Fate, please tell us the last one. Covalent. And someone now, tell us the little cheat code to remember, how do we know, just by looking at the formula of a substance, which one is which? Which one is occurring in that formula?
AI is metal.
You probably, thank you, I do need to cross that T. Thanks, Taylor. What do I look at about the formula? If I just if I say this is the formula worth considering, how do I know which of these?
Metallic is by itself.
Okay, so metallic, it's only what? Where someone's looking up there, you're at least looking in the right region. Yeah, the periodic table is where we look. If it's only metals, that's metallic bonding. What is this one?
Magnesium.
Which is a metal. This is, what's his name?
Chlorine.
Chlorine, which is a?
Gas.
It's a non-metal. So if it's a metal and a non-metal, which of these kinds of bonding is holding it together? We talked about this last chapter. Well, there's only two left, and the current decisions are split half and half. Why don't we actually think about it? How do you know, Taylor?
Because that's the only one that no one said yet.
Actually, they have, but you're right. It is ionic. And what is the rule? Let's say the rule then. In metallic, let's give an example. Iron. If it's just iron, that's a metallic bond. The reason it can be just this one and it's bonded is because there's more than one atom of iron, right? Just because it's only iron doesn't mean it's only one atom of iron. It's just multiple atoms of iron. They're all bonded together. That's a metallic bond. In this ionic bond, we have a metal bonded with a nonmetal, in this case two nonmetals. And in a covalent bond then, give me an example of this one. Or tell me the rule first, and then let's give an example. Two or more metals, a metal and a nonmetal, two or more nonmetals. So give me an example. Give me some substance that actually exists that is made of, let's say carbon monoxide. Very good example. Carbon monoxide. Carbon monoxide. Carbon is we're on the periodic table, it's a what? A what kind of thing? It's a nonmetal. Oxygen is a nonmetal, and therefore that's a covalent bond. Please remember this. So let's write the rule now. Two or more metals. Metal plus nonmetal. Two or more nonmetals. Okay? That's review. That wasn't supposed to take 7 minutes. I don't think it did take 7 minutes. All of these are kinds of bonds, yeah, bonding. Redefine bonding for me in layman's terms. Just give me a second, Gabe. Redefine bonding for me in layman's terms so we can all be on the same page here.
One attaches to
Sure, attaches is an okay word. I don't mind that at all. It's as good as anything else. They're stuck together. They are combined. Yeah, that's what we would. That's probably what the book says. But yeah, those have bonded. Meaning now there's a force of attraction between them. Just like you and your wife or husband have a force of attraction between you. That is bonding. Fate thought it was funny at least. Thanks, Fate. Okay.
That has so many lives.
Fate, yeah, typical. Yeah, let's hear it, Gabe. What's your question?
So carbon monoxide.
Shay, be quiet. What, Will? I want to hear your opinion. No, you're not. This is not a safe space. Well, I don't know why you would ever think that. You've been here for 9 months. Yeah, yeah. You mean from talking about inappropriate fluids and stuff? Yeah. Okay, I want to hear yours.
So is carbon monoxide called carbon?
Hey, listen, Gabe has an actual question. He's going to answer it once you're done interrupting him, and so am I. Gabe, would you please answer your question without being interrupted by anyone, including me?
Is carbon monoxide called monoxide because there's only one oxygen in carbon dioxide?
We're going to get to that. In fact, that's this chapter. The question was, is carbon monoxide called this because there's only one oxygen? And the answer is yes. We will get to how we do that. And that's the thing we do this chapter. The math. Where we would have math on a test is how do we tell what this thing's name is just by its formula, and how do we tell what its formula is by its name. We talked a little last time about, let's do, let's draw down here a model. We have here example. We have here, I'll put rule. And then we're going to have here a model. What would the model of metallic bonding look like? This was a question on your test. I really hope that you can answer this. There you go, the sea of electrons. So we have multiple positively charged metallic atomic nuclei, multiple positively charged metallic atomic nuclei, and shared between all of them are the valence electrons. A sea of electrons. All of them allow their electrons to flow among themselves and between each other, etc. That's why the properties of a metal exist. That's why when you hit a metal, it stays the way you hit it. That's called malleable. Why electricity and heat flow easily through metals, because these electrons can flow from one to another. And it makes that noise. And that's why if you listen to a metal, if you hold a quarter up to your ear, it goes whoosh, whoosh. No, it does not. I mean, I guess if, just like the seashell thing, what you're hearing is an echo of your own little ear wigglers.
That's not true.
No, yeah, I don't know what I'm talking about.
I actually thought that
Okay, so let's draw a model now of the ionic bond. Let's do magnesium chloride specifically. What should I draw first?
magnesium.
Okay, sure. 1 magnesium. Hey, this relates back to your bell work. How do I know it? Just looking at the formula, how do I know it's 1 magnesium?
Because there's no...
Yeah, what's his name? There's no little number. What's the little number's name? BT dub.
Exponent.
It was on your bell work. Subscript. This is called a subscript. This is called a subscript. It is, and just as a little tiny side note, on the bell work, anytime I put something on the board for this chapter, it's going to be big, because that platform does not let me make subscripts. So just pretend it's little baby. So what you would see on the bell work is this, but that's not how it's supposed to be. That actually means this is what I would have written if that thing let me. Anyway, so that's the little subscript. So since it doesn't have a subscript at all, what is its subscript? Someone is going to say 0, and why are they wrong? If I multiply mg by 0, how many mg's are there? 0. Yeah, it's 1. If there's no subscript, write this down please, because someone's not going to get this if they don't write it down. If there's no subscript, that's 1 of that atom. It is not 0. Hey, what element is there 0 of in my formula I have up there? MgCl. What element is there 0 of? Everything else. All 116 other elements are 0, so I just don't write them. That means what I'm getting at is that the subscript is not 0, because everything else would have subscript 0. The subscript, not having a subscript, means it's 1. This one, though, there are of chlorine. How many should I draw of chlorine? 2. How do you know? This is the bell work. Yeah, that little subscript is how many there are. Actually, more specifically, that subscript tells us the ratio of chlorines to magnesium. What is the ratio of chlorine to magnesium? 2 to 1. 2 chlorine for every magnesium. And that's true if we go in there and we just get out the jar that says magnesium chloride on it and we put our hands in there, that whole handful, for every 1 magnesium, there are 2 chlorines. It's true whether you just have 3 atoms or if you have a dump truck load of magnesium chloride. That's the same ratio throughout. It's actually telling us the ratio. Anyway, so in this model, in ionic, do you remember what verb has happened? How many valence electrons did magnesium begin with, and where do you look? Let's actually ask that in the other direction. Where do I look? Where do I look to find how many valence electrons magnesium began with? The periodic table. How many did it begin with? Let's find magnesium, number 12, and tell me how many valence electrons did it start out with. How did you know that? You're just a wizard? He looks like a wizard because of his long flowing hair and beard, yes. It's an alkaline earth metal. It's in group 2 and therefore has 2 valence electrons. Boop, boop. But how many does it want? It wants 8. Okay, so it has 2 valence electrons on the outside. 1 layer down, it has 8. So what could this magnesium do? In fact, what has it done to get to 8 valence electrons? It bonded. And bonding is it gave these 2 valence electrons each to a chlorine, which had, each chlorine had 1, 2, 3, 4, 5, 6, 7. How would we find that out? Once again, the periodic table. Now, each chlorine has 8, the magnesium has 8, and everyone is more stable. I sometimes say happier. That's an allegory. I mean they're more stable like this. Why do things bond? Why bond?
Because happiness.
No. Don't think like that. That's a nice little allegory or metaphor or catchphrase, but these things cannot experience happiness. Why bond? They become both. No, they are not alive. Both become more stable. The reasons for this are in the realm of quantum mechanics that we're not going to talk about. We will talk about in chemistry, but both of these, because of the nature of the universe, are more stable if they have a full set of valence electrons. And so both become more stable, both here meaning the group of magnesiums and the group of chlorines all become more stable when they have a full set of valence electrons. In this, what verb has happened here? The magnesium has done what to its valence electrons? Bonded. No, not to its valence electrons. It has done what with them? Got rid of them. It's given them away. The magnesium has given electrons. You should probably write this down. The magnesium, this is really still all review, but you still should write it down. The magnesium has given valence electrons. The chlorines have received or taken or accepted valence electrons. Why are they stuck together then? What holds them together? Love. No, you can't just say the bond. What is the bond? Why does the bond exist?
The strong force.
No, not the strong force. If this thing gets rid of 2 of its negatively charged valence electrons, it now has a 2 positive charge, yeah. It has given away 2 valence electrons. Please write this down. Has given away 2 valence electrons, so now it has a 2 positive charge. Each of these chlorines has gained an electron, so they now have a 1 negative charge. And what now that we have said that, tell me why they are bonded. Because of the electromagnetic force, because they have, not just different, but they have opposite charges, and the missing piece here, opposites attract, right? That's why Gabe and I, with our inherent instability, I am bonded to someone who's very stable, and Gabe probably will have to be too. Otherwise, they'll just, you know what I mean? This is another allegory. Sometimes unstable people do bond, but I'm serious. You don't want to go there. This is true. This is true for all of them. This is true for all of these bonds. This is true for all of these bonds. They bond to become more stable. It's true of the metallic bond. It's true of the ionic bond. Let's look at the covalent. We have here a carbon and an oxygen. Both of these things are nonmetals, and they're going to share between them. How many does oxygen start out with? How many valence electrons does oxygen start out with? It starts out with 6. That's 6 valence electrons. What about carbon? Just ignore that. What about carbon? It starts out with 4. 1, 2, 3, 4. Now check it out. These valence electrons, ooh, this is actually going to have to be like, that was a pretty good music. Why? Oh, this one needs to, there we go. This one, now look, they are sharing these electrons in the middle. Carbon has shared 2 of its electrons, oxygen has shared 4 of its electrons, but they're sharing. And so now the carbon is acting like it has 1, 2, 3, 4, 5, 6, 7, 8, because they're sharing these 6 in the middle. So carbon's acting like it has 8. How many do they want to have, BT dub? By the way, you know about that? They want to have 8. How many does carbon have now? 8. How many does oxygen have now? 8. It has 8, because they're sharing these 6 in the middle. This region here, this is not a Venn diagram, but this region here represents the ones that they share. So what's holding these together? Well, these electrons are attracted to the carbon, and these electrons are attracted to the oxygen. All these electrons are attracted together. And once again, it's still the electromagnetic force. They're sharing. They have become more stable by bonding, in this case, by sharing. This is probably the better analogy for marriage that we were talking about earlier. Marriage should probably not be give and take. This is how your relationship with like the gas station attendant at Wesco works. Like you give them $2 and they give you, you give them $6 and they give you an energy drink. That's that relationship. This one really should be sharing. You give them your love and they give them yours, and that's beautiful. Just like Mr. Gaston and Dude, probably, I would guess, they love each other.
Mr. Gaston sometimes gets hecka heated at them.
Yeah, but that's part of love, Taylor. Yeah. Anyway, you're being videotaped, Taylor, so I would keep things that you don't want everyone to know to yourself. So we have 3 different kinds of bonding here, which hold atoms together. Yeah? Write that down. Bonding holds atoms together. We have the metallic bond. We have the ionic bond, which is formed between metals and nonmetals. And we have the covalent bond, which is formed between nonmetals. Okay? Each of these has a chemical formula. A chemical formula tells us the ratio of one thing to another in that substance. Sorry, what? Hey, we're trying to do something here. So would you please stop talking about that and start taking notes? The part of this chapter that people suffer with, I wouldn't say people are bad at it, but the people have a hard time with, is that how do we find out how many, for instance, how many chlorines, you remember this little process, how many chlorines it takes to make the magnesium stable. That's the part that we get into now. First, let's talk real quick about bond polarity. So I'm gonna erase. Does everyone have, for each of these things, the type of bonding? Does anyone not have, raise your hand if you have not written down the 3 types of bonding. If you haven't, you need to do it now. Does anyone not have the example formula? Iron, magnesium chloride, carbon monoxide. Does anyone not have the rule for each of these types of bonding? Taylor, do you not have the rule?
I do.
Okay, so, and then the model is this little picture that tells us how it occurs. And then on the bottom, this is Hunter, this is the big idea for this entire chapter. Why do things bond? To become more stable. Because they want to? No, they don't want anything. The universe says they are more stable when they have 8 valence electrons. Do you remember what's the name of that rule? We talked about it in the last chapter. What is the name of the rule that says they're more stable when they have 8 valence, or rather, when they have a full shell of valence electrons, when they have a full orbital of valence electrons? What was that called?
Oh, octet.
The octet rule. What number does octet remind you of?
Octagon
8. Means they want 8, most of them. There are 2 exceptions. Hydrogen and helium, since they only have 1 energy level, and the first energy level can only have 2 electrons, hydrogen and helium only want 2, but everything else on here wants to have 8 valence electrons. So we call it the octet rule. They're more stable. More stable. When I say they, what am I talking about? Who?
Electron.
No. Elements. Every element is more stable with 8, I'm going to put a star next to that, valence electrons. And the star means except, who did I just say? Hydrogen and helium, because they only have one valence electron. Or I'm sorry, they only have one electron orbital, and so they only need two valence electrons to become most stable. The octet rule. This is a truth of the universe. Like I said before, we're not going to talk about why this is true, why they're more stable with 8. It has to do with their energy harmonics, but it is true. They're more stable when they have a full shell. Bond polarity, as I said. So head this section. I assume you take your notes in sections. Head this section bond polarity.
I don't. I usually just write down.
Yeah, I bet. Okay, head this section bond polarity. Polarity is a noun meaning to have the property of being what? Guess. Polar. Polarity. To have the property of being polar. Not cold. Why would we say cold? Why would we associate polar with cold? Because the Earth has poles. The Earth has poles, and those poles are on places of the Earth that get little sunlight, so they're cold. For an atom, for an atom to be polar means that it has poles. I'll give you two examples. We're going to have two examples here. We're going to have two examples here. We're going to have the molecule chlorine, and we're going to have the molecule water. Both of these are bonded how? What kind of bond does both the molecule chlorine and the molecule water have? What kind of bond is that, and how do you know? This should not be this hard.
Oh, they're covalent.
They're covalent, Gabe. Good job.
Because they have two or more.
Hey, it's actually time to stop talking to each other just for no reason at all and start paying attention. So these examples are covalent. They have to be. In fact, this only happens only in covalent bonds. Meaning they've done what? What verb? They are doing what with their electrons? Sharing. Yes, good. Okay. So in both of these covalently bonded molecules, yes, Cass?
Okay, so something that I just thought of, so covalent, the word valence.
Yeah.
Valence bonds.
Yep.
Co-sharing.
Yep, that's exactly right. That's exactly right, yep. Covalent, as Kesson correctly points out, means that they are together. Like when you cooperate, stop talking to each other. Thank you. When they are cooperating, they're not, but when you cooperate, you're operating together. When these have a covalent bond, they have a valence together. They have a valence shell of electrons together. So in both of these, they are sharing electrons. Let's diagram them. What's that little line represent in the middle, do you reckon? A bond. A bond. In this case, that line represents two electrons, two valence electrons being shared. If we could draw it a different way, let's draw it a different way. How many valence electrons should chlorine have? You should know this by now. 7. 1, 2, 3, 4, 5, 6, 7. How many should this one have? This chlorine? 1, 2, 3, 4, 5, 6, 7. But look, they share these two, and so now your boy is happy and your other boy is happy. And these two that they share is symbolized by this dash. We can show them in either way. This is called a Lewis structure, and this is called a space-saving model or maybe a stick model. But they share those two electrons, and that's represented by a bond. Same thing here. Oxygen has 1, 2, 3, 4, 5, 6. Sorry, I should have drawn it like this. 1, 2, 3, 4, 5, 6. And then the hydrogens each have how many? 1. But remember, they only need 2 to be happy, so keep that asterisk in your mind. They only need 2 to be happy. So there's the hydrogen sharing 1, hydrogen sharing 1. Hydrogens have 2, which makes them happy. Oxygen has 8, which makes that one happy. They are sharing, but they're doing that to gain what? Stability. Stability. Now, here's what makes it polar. You're an electron. Yeah? So make yourself an electron. What's your charge?
Positive and negative.
Actually, that's totally wrong, Gunnar. Nothing wronger has ever been said than that. You're an electron. What's your charge?
Positive, negative.
Let's try one more time.
Neutral.
You guys ever quit your job and it's basically Monday? Yeah, y'all are electrons. Maybe if you listen to the question, you can answer it. You are an electron. What is your charge?
Negative.
Negative is correct. Most of you said negative. Please write that down because someone already said 9 wrong answers. So everyone write that down. Electrons have a negative charge. Thank you. We've been talking about this for 4 months. Electrons have a negative charge. Who are you attracted to? Don't answer that as a truth. Positive. Yep. That's very good, Gunnar. Yeah. You are a negative electron. You are attracted to things that are positive. Okay? So this is you. Hey! This is you. You have a negative charge. What are you attracted to in this situation?
The wall that has a positive charge.
Please stop. Please stop just saying random things. You have a negative charge. Of these things, what about this attracts you? Once again, what charge are you looking for? Positive. So the what part of either of these atoms attracts you?
The protons.
Okay, which exist where? Nucleus. Okay, so I'm trying to make this easy for you, and I literally cannot dumb this down anymore. You are a negative electron. You're attracted to the positive nuclei. Yeah? How many protons are in the nucleus of a chlorine atom? And how do you know?
There'd be 617 because it's the atomic number.
Yeah, it's 17. It's 17. So there's 17 electrons in here. I'm sorry, 17 protons in here. This marker is dead. 17 protons in here. That's supposed to say 17. Who of these twins are you more attracted to as a negative electron? Nope. Let's try to answer truthfully and stop saying inane things. Who, if you're a negative electron, of these are you more attracted to? It's a trick question. Neither. You're attracted to them both equally. That's the point. Equal attraction. Now, shh. In this situation, you again are an electron. In this situation, you again are an electron. How many protons exist in the oxygen's nucleus? 8. How many exist in the hydrogen's nucleus? 1. Who are you more attracted to? The oxygen. Okay, so in this case, this has an equal attraction. So we call this, we call this non-polar. There are no poles because the electrons are not attracted more to one or the other. But in this one, who are you more attracted to again? Oxygen. So if you spend, because you're more attracted to them, just like you spend more time at your girlfriend's house because you're attracted to her, if you spend more time with the oxygen and you're an electron, what charge does this end of the molecule take on? You and your homies are more attracted. You're negative, and you're more attracted to this end. What charge does this end take on if you spend more time over here as a negatively charged? This has a negative charge. We use this little Greek lowercase delta. Let me write this in a different color so it actually shows up. This Greek lowercase delta negative up here becomes delta positive, and this is called a polar, nope, do not leave, write this down, a polar bond. Because it has poles. Has a positive pole where you don't spend as much time, has a negative pole where you spend more time. Polar.